Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be introducing the Hamilton's equations and Hamiltonian systems and how the Hamiltonian is related to the Lagrangian via the so-called Legendre transform. So in this module we will straight away start with the idea of Hamilton's equations. Okay, we will see that these are my Euler Lagrange equations with n degrees of freedom. N degrees of freedom. So we know that each Euler Lagrange equations for each degree of freedom or each variable will be a second order differential equation. So we have the following holds: d dt of partial L partial qj dot minus partial L partial qj, this is 0, j from 1 to n, and where my L is the Lagrangian q comma q dot comma t is the Lagrangian. Okay, so then we know that we are familiar that this is a second order differential equations for n ODEs in the variable q1, q2, qn, right? And we are now going to convert this second order ODE into first order ODE. So now we will have 2n equations rather than n equations. So suppose now we introduce the conjugate momenta which we have seen in one of our previous modules. So consider the conjugate momenta. Right, so Pj, which is partial L partial Qj, and this is for j 1 to n, and we can also rewrite this conjugate momenta in an alternate fashion, that P. Now rather than talking about each component, let us talk in the vector notation. So vector P is grad of q dot, and this is going to be of L of q comma q dot comma t, right? So what we have is, so the original equation was Pj was del L partial Qj dot. So now we have written this in the vector notation. So now if we eliminate this variable q dot, so eliminate q dot, the variable q dot or the generalized velocity, using our Legendre transform q dot is grad p. So now we are using the Legendre transform to introduce the so-called Hamiltonian h of qpt, and we see that we now are going to describe the Hamiltonian. This is our first introduction of this function, which is the Hamiltonian. So what is Hamiltonian? So let us give the definition of this function Hamiltonian. So we see that the function h of qpt, which is which is the Legendre transform of the Lagrangian transform of the Lagrangian. See, the Lagrangian variable was described in the form of with respect to the independent variables q, q dot and t, and now we have the Hamiltonian, which is now described in terms of q, p and t. So there is no velocity component in Hamiltonian, which we expect that the eventual equation governing the Hamiltonian should be first order, right? So what we have is that is the Hamiltonian of the system. Hamiltonian of the system S, right? And we see that h of q p t is q dot p minus L of q p t. So h is so this is our regular Legendre transform. So h is q dot p minus L of this function. So that's our regular Legendre transform definition. Okay, so then throughout this discussion, we can see that my active variables are both q dot and p. Why? Because we can see q dot and p are appearing in these equations, and so which means correspondingly our passive variable, a variable which is not appearing explicitly in this equation, is q, right? So let us now use all the relations for the Legendre transform. So we see that now my Hamilton's equation coming straight from the Legendre transform, Hamilton's equation q dot is grad p h of p q t, and p dot is grad minus grad q h of p q t, right? So then so these are my Hamilton's equation, and that is what we have. So now we can see that these are clearly these are first order differential equations, right? So these are explicit in time t, and t of course similar to q, t of course is a passive variable. So explicit in time dependence, so t is a passive variable, so which means the time dependence is going to follow as partial L partial t is minus partial h partial t, right? So I have that L has time dependence, and so has h, right? So both L and h have thus following time dependence. Okay. So then let us now, so mathematically the idea is clear. Let us look at this idea through some quick examples appearing in classical mechanics. So the first example that I have is the case of the simple pendulum. So this question says find the Hamiltonian and the Hamilton's equation for the simple pendulum. Okay, so we have the Lagrangian L given by t minus v, and we see that the Lagrangian is half m a square theta dot square. So that's my kinetic energy, plus mga cos theta, right? And for this we have p theta given by partial L partial theta, and this is ma square theta dot, or we can, so this is my, well, partial L partial theta dot. My generalized coordinate in this Lagrangian is theta hai. So my conjugate momenta p theta is as follows, or I can write theta dot as p theta by ma square. So which means that now p theta by so then based on our definition we can introduce our Hamiltonian. There is only one variable in the form of a generalized coordinate that we have to worry about, that is theta. So our h, our Hamiltonian h of theta comma p theta is theta dot p theta minus L, right? And we can write this as p theta by ma square times p theta minus ma square by 2, well, so we have used the definition, so minus ma square by 2 p theta by ma square whole square minus mg a cos theta. So what we have is that this is p theta square by 2 ma square minus mg a cos theta. So after all the simplifications, so my Hamilton's equation, so we see that my Hamilton's equation will be in the form of q dot and p dot. So we will have to write an equation in terms of, in this particular example, in terms of theta dot, which is our q dot, and p theta dot, which is our p dot. So as I just said, my Hamilton's equation is theta dot given by partial h partial p theta, which is p theta by ma square, and p theta dot is minus partial h partial theta, which is minus mga sine theta. Okay, so then I can rewrite, so well, so these are my two first order ODs as far as the system is concerned. We can again use our regular method by eliminating one of the variables and come back to another ODE. So if we eliminate p theta and solving, we see that our system is theta double dot plus g by a times sine theta, which is 0. So this is our Lagrange equation for the system, which is, we can quickly check using our Euler Lagrange equations. Okay, so then, so as far as an example is concerned, so that should clearly explain how to utilize the concept of Hamiltonian and write the Hamilton's set of Hamilton's equations. So let me quickly discuss the properties of Hamiltonian. The properties of Hamiltonian. The first one is the Hamiltonian is identical. Hamiltonian is identical to the energy functional. So we can quickly relate Hamiltonian to the energy of the system, the energy functional. Okay, why? Because this functional is dependent on the variables like q and p, which are themselves functions of time t, right? And so our energy functional h can be written as, again using Legendre transform, is qj dot pj j from 1 to n minus L of q comma q dot comma t. And we see that for the autonomous system, our H, autonomous system implying when there is no explicit time dependence, which means the time derivative will vanish, or my H is our regular Hamiltonian, or for autonomous system this is equivalent to the conservative system, right? So this has no time dependence. Okay. So what we have is that H is a constant of motion. Okay. Now suppose our Hamiltonian Q comma P, H is a motion of the system. So suppose what we have is, let me write this statement and I can explain what is going on. So we have, so suppose this is a motion of the system. Okay. So suppose what we have is dH dt, the Hamiltonian can be written as summation j from 1 to n partial H partial Qj times Qj dot plus summation j from 1 to n partial H partial Pj dot, right? And now I can introduce, well, so Qj dot is nothing but partial H partial Pj, and Pj dot is partial H partial Qj using our Hamilton's equation, right? So what we have is, so I'm going to use my Hamilton's equation in both these constraints, and we see that this is summation j from 1 to n partial H partial Qj times partial H partial Pj plus partial H partial Pj. I'm just replacing all my all my derivatives of the independent variables with using our Hamilton's equation. So this is partial H partial Qj, and we have a minus sign because of the Legendre transform gives a minus sign. So then we see that this summation is nothing but 0, because both these terms they cancel each other, and we see that in this case when the Hamilton's equation is the equation of motion, we see that there is no explicit, the Hamiltonian is constant with respect to time, or the Hamiltonian is conserved, right? So what we have is, the conclusion of this small exercise is that for autonomous system we have that the Hamiltonian is conserved. Right? And for standard, we have that for standard conservative system S, we have that H of P comma Q is, this is for a conservative system, it is equal to the kinetic energy plus the potential energy V of Q, right? We expect the potential energy only to be a function of generalized position or generalized coordinate. So this is for the conservative system, this is our total energy. So at least the Hamiltonian has a physical meaning, a physical counterpart in classical mechanics. Lagrangian typically cannot be associated with a physical meaning, but the Lagrangian is related to the Hamiltonian using our Legendre transform. So then let us again look at one more example. The example is we need to find the Hamiltonian or the Hamilton's equation. The Hamilton's equation for inverse square orbit, right? And we need to find, so again we know that we will find these quantities via the Lagrangian. So we know Lagrangian is t minus v. This is for the inverse square orbit, right? So we know that the orbit problem is conservative. The orbit problem is conservative. So what we have is that the Hamiltonian is t plus v, where we have, the moment we write that the system is conservative, we can quickly associate the Hamiltonian to be the total energy t plus v. So where my kinetic energy T of r comma theta is half m of r dot square plus r theta dot square, and my V of r is minus m capital M g by r. So that is my V of r. And from here I can describe what is conjugate momenta. P of r is partial L partial r dot, and we see that this is mr dot, and my P theta is partial L partial theta dot, and we expect that this is mr square theta dot, right? And again we can write down this time the Hamiltonian. So well, we already have all the expressions for kinetic and potential energy. We are going to write down the Hamiltonian. See, to begin with, the Lagrangian had two variables, r and theta. We have now introduced two more variables, pr and p theta, and the Hamiltonian should have all these four variables. So eventually the Hamilton's equation should have four equations for the two generalized coordinates r and theta, right? So we have the Hamiltonian as h is equal to t plus v, which is given by half m r dot square plus r theta dot whole square minus m capital M g by r. And we see that this is going to be pr square by 2m plus p theta square by 2m r square minus m capital M g by r square. Well, r. So we only have an r. Okay. So well, now we can start to write the Hamilton's equation. So we see the Hamilton's equations. Hamilton's equations are, first we have the equation for r. So r dot using our Legendre transform is partial h partial pr, right? And we get that this is pr by m. And similarly my theta dot will be partial h partial p theta, and we see that this is going to be p theta by m r square. So that is what we had, p theta by the well, we are treating pr and p theta to be independent variables here, right? And we have that pr dot is going to be minus partial h partial r, and this is going to be p theta square by m r cube minus m capital M g by r square, right? And we have p theta is given by minus partial h partial theta, again using Legendre transform, and we do not explicitly have theta in our variable, so this is going to be 0. We can see that in this equation here. right? R is appearing, but theta is not appearing explicitly. So these are my two equations, set of four equations. So now we can write the momentum conservation. So, I want to now introduce some related concepts of momentum conservation using the system of Hamiltonian. So momentum conservation. So what we have is that from Hamilton's equation, we have Pj dot is minus partial h partial qj, and we have that since if we have that this quantity is 0 on the right hand side. So if partial h partial qj is 0, or qj is cyclic, cyclic implying that, we are using the idea used in Noether's theorem, where one of the variables is cyclic. So then we expect that the corresponding generalized momenta is a constant of motion. It's a conserved quantity, right? So this is coming directly from the Noether's theorem. So then again, if we look at the same perspective from the Lagrange equation, so the first idea was from Hamilton's equation. Then from Lagrange equation, we see that if partial L partial Qj is 0, then Qj is cyclic. Or Pj is constant. Pj is constant here. Okay, so then so we will be using these ideas shortly. Now I want to state the fact that in when we were talking in terms of Lagrangian, we only had the generalized coordinates q and its velocities q dot, and those were the independent variables, and of course time was there. Now we have a set of variables such as the generalized coordinates q and the coordinates generalized momenta, which is p. So now what we have is the Hamiltonian space. So we call these new set of variables q, p, and t as the Hamiltonian space. Hamiltonian space, right? So we have that. Suppose the system S has generalized coordinates q and conjugate momenta p, right? And we have the Hamiltonian given by h of q comma p comma t, right? We see that the initial values, if the initial values suppose are given in the system. So suppose the initial values are given, so q and p, right? So we can subsequently write q and p at subsequent time of interest. Our values are qt and pt. So this is going to be uniquely determined by uniquely determined via the Hamilton's equation. Right? And what we see is that we talk about, so the Hamilton's equation describes the trajectory of the particles in the so-called Hamiltonian space. So the motion is geometrically determined by by the Hamiltonian phase space. Okay. Then the other idea that we are just rotating these ideas, we are just, let me just repeat the statement that now the Hamiltonian is a 2n space for n particles rather than n space for, as in the case of Lagrangian. Why? Because now the Hamiltonian or the Hamilton's equations are first order ODEs. So I think I am all out of time at this point for this module, and in the next module we will be looking at some examples and how to utilize these ideas of Hamiltonian and Hamilton's equations. So thanks so far for listening.